Hi, my name is Ilan Gur. I'm a program director here at ARPA-E, and I'd like to tell you about a program we recently launched at the agency called AMPED, Advanced Management and Protection of Energy Storage Devices. I'm the program director for the AMPED program, and I'm going to spend the next 30 minutes or so giving you a tour of the program, telling you a bit about the motivations for the program, the technical vision, and highlighting a number of the exciting technologies that we're funding under the AMPED effort. Before we jump into AMPED specifically, I want to just give you a backdrop. This is a map of the 14 focused programs that we funded to date at the agency. What you see is that we generally split up the energy landscape into two halves, the transportation sector and the stationary sector. And we've got a number of programs that sit in each of those areas, and also some, like AMPED, that kind of span both the transportation and stationary sector. At the bottom of the slide, I'm just highlighting the main mission thrusts of ARPA-E as an agency. For those who don't know, ARPA-E focuses on supporting high impact, over the horizon advanced technologies that can make a significant impact specifically on one of these four areas. So the first is energy security, and specifically we're talking about reducing our dependence on foreign energy imports, increasing energy efficiency in the U.S., reducing emissions related to energy use, and then finally, generally improving our position as a country in competitiveness of technologies for energy. So when we think about these mission areas, it's pretty easy to see that energy storage can play a big role, both on the transportation side and the stationary side. And so early in the agency, we ran 3 programs that focused on energy storage. On the transportation side is a program called BEAST, which focuses on trying to develop new high energy density battery systems, specifically to allow more portability for future electric vehicle designs that could give us very high range at a reasonable cost. On the stationary side, we don't care so much about energy density and portability. What we care about is just the cost of energy storage. And we have a program called GRIDS, which focuses on dramatically reducing cost of energy storage systems up to about an order of magnitude versus the state of the art. And finally, we have an SBIR program that's supporting efforts in both of those areas. And so when we stopped to analyze, before creating AMP, when we stopped to analyze the portfolio of efforts that we were supporting at the agency in energy storage, what we realized was all of our efforts are really focused on what I would describe as sort of chasing the dream of energy storage. And it's an important dream. But the dream is basically, what is the next great battery chemistry or architecture? Right? And so if we think of the history and all the major developments in energy storage or batteries, we can think about new chemistry platforms. We go from lead acid to nickel cadmium to nickel metal hydride, and now lithium ion, which has really dramatically improved our capabilities in energy storage. And so that's a very challenging. Thinking about what's the next big system, for instance, after lithium ion on the transportation side, is a hugely important question. But what we don't want to lose sight of as we're chasing this dream is the fact that when we look at the battery systems that we're using today commercially, the best state-of-the-art battery systems, we don't actually use them as well as we could. And we're not really leveraging the full potential of these battery systems. So that's sort of the origin of AMPED. And let me tell you a little bit more about that problem that I'm describing. So this is a very simple block diagram. And what it's meant to show is thinking about how we design a battery system. Now, this is applicable both for the electric vehicle case or the storage case. Generally, throughout this talk, I'll use electric vehicles as an example because I think it's something that more folks can relate to. But everything I talk about is applicable to the grid storage side as well, and AMPED is really focused on both sides of this problem. But if we think about designing a battery for an electric vehicle, what we ask ourselves, first question you need to ask yourself is, how much energy do I need to deliver for the load? How big does the battery have to be? And you can basically calculate that. In a vehicle case, you say, well, okay, how much energy does it take to move the car, and how far do I want to move the car? And then I'll know how much energy I need in my battery. And so you can look at the size of the car, the aerodynamics, and say, well, okay, it takes, let's say, 200 watt hours to move the car 1 mile, and you multiply that by the range, and you say, okay, this is the amount of energy storage that I need. And you go out and you buy a bunch of battery cells of that capacity. And so, okay, we're done. Well, we're not done, right? If you look at a conventional system today, what you find is there's the capacity to move the car, but the system will also include additional capacity. And this can be as much as twice as much or more capacity beyond what you actually need to drive the load. And so why do we need this capacity? Well, we basically realized that if we operate the battery at the extreme limits of its operational range, that's when we have the biggest issues related to degradation, related to reliability, related to safety. That's where a lot of the mechanisms that can really ruin the battery come into play. And so what we do is we have a very conservative design. We put extra capacity in there so that we're only utilizing in a very small middle range. Well, small or larger depending on the application, but certainly utilizing just a middle range and having this extra cell capacity around as a buffer. So we have the base capacity. We added on some overhead capacity, but we're not done yet. We still need to build a battery system and a module, a pack. And that's going to be the balance of systems. Include the physical protection of the battery, the thermal management, the power management of the battery. And at the end of the day, when you add up all of the extra stuff that we've designed into this whole system, and you compare it on a cost, weight, and volume basis with just those cells that you needed to move the car, what you find is that on a cost, weight, and volume basis, the system can be as much as 2, 3, 4, 5 times as big, heavy, expensive as just that base capacity cells would be. And so there's a big over-design in these systems. And here's the kicker. It's not like by designing very conservatively, we've actually solved all the problems that we're trying to address. So despite the extra weight, volume, and cost, we still have limitations in performance. The lifetime of the battery is still a concern. Safety, even in the most conservatively designed systems, safety is still a liability. And across the board, it's certainly a perceived liability. And we're also limiting performance. So we often limit power, charge rates, because we don't want degradation mechanisms to come into play. We talk about things like dual use or secondary use of batteries, but that's still very much limited by concerns of reliability. So as an example there, I might want to plug, I buy an electric car, it was very expensive, and so to offset some of the cost of the battery in that car, what I'd like to do is when it's sitting in my garage, I'd like to plug it into the utility grid and let the grid access some of my storage capacity for different ancillary services, and they'll pay me for it. I know they'll pay me for it. What I don't know is what's the cost of the additional risk to the reliability of my battery pack for the primary application, driving the car. And because I don't know that, I can't do the cost, I can't do the trade-off analysis, and we just don't do it, right? We just decide, okay, we're going to limit the performance. We're not going to do it because we're concerned about what it might do in life. So the AMPED program has basically asked, well, can we do better, right? Again, the over-design here, depending on whether it can range depending on whether you're an electric vehicle, a plug-in vehicle, or a hybrid. The amount of over-design and the amount we're limiting performance varies, but it's certainly significant across the board. And so to answer the question of can we do better, we wanted to think about, well, what's the technology basis for why we have to design so conservatively to begin with, right? And so I'm sort of cheekily terming that question, well, what are we scared of? What are we protecting against? And when you look at what we're protecting against in terms of degradation, in terms of safety and reliability in batteries, what you find is that the things that lead to degradation and safety issues in batteries are basic physical, chemical, electrochemical reactions and phenomena, mechanical issues that are happening inside the cells of the battery pack. Okay, so these are things like reaction of the electrolytes because of temperature or electrochemical potential at the electrodes of the battery. Things like mechanical defects, plating lithium metal and getting dendrite formation, which leads to internal shorts in the batteries. It's a mechanical issue that develops related to the electrochemistry. It might have to do with stress of the electrodes and cracking internal cell defects that come from mechanical, from manufacturing, etc. This is not a comprehensive list, but this is a few of the examples. And so what was interesting to us from a technical perspective when we started thinking about AMPED was, okay, we design our systems very conservatively, largely because we're trying to protect all of these really intricate physical things happening inside of every cell in a battery pack. And yet, we don't actually look and monitor any of those things directly, right? What we monitor is basically what's easy to monitor. We monitor temperature, we monitor voltage, and we monitor current, and that's about all for battery management. And we don't even monitor, right? You'd say, well, if you monitor those things inside the cells, you might get some insight into these physical phenomena happening inside the cells, but we don't. We generally monitor groups of cells. We have an indirect and basically a low spatial resolution measurement, and we use that measurement in the battery pack to basically decide how we're going to operate it, to design our systems, even though what we really care about are physical things happening inside the cells. And so the picture that I have is basically this. We're sort of driving blind. And because we're driving blind, rather than right-sizing our systems and controlling them optimally, we have to oversize our systems and control them conservatively. So the question that got us excited here at ARPA-E was the question of, well, what if we could remove the blinders? What if we could actually see directly the things that we're scared of happening inside of cells in a pack? And that might sound kind of crazy, but I'll give you a few examples of both potential capabilities there, but also interesting questions of what would happen if you could monitor what's happening inside of cells. This is an example of temperature. I mentioned that we measure temperature outside of cells. What you have here is temperature as a function of time and an event where you're dramatically increasing the current in a cell. And what you see in the blue curve is what you would normally measure in a battery pack today. That's at the surface of the cell or outside of the cell. And you see a steady rise in temperature. And then the red and the green curves show actual direct temperature measurements. This is work done at Johns Hopkins. Being able to monitor the temperature inside the cell at the electrodes. And what you find is if you monitor inside the cell at the electrodes, you can see a much sharper behavior. You can actually read the real temperature changes happening in the cell. Not only that, you can see that there are different temperature changes happening at the two electrodes of the cell. And so this might give us an opportunity to, for instance, detect bad events, whether it's reactions or safety events, quicker, but also potentially get more information about what's happening inside the cell, some of the degradation mechanisms that might be happening for every charge and discharge profile that we're running. And so it's an interesting question, right? What would we do with this more information? How much more valuable could it make us? That's an example of temperature. I'll give you another example. We measure voltage, and we even measure voltage of almost every cell in most packs. What we don't measure is voltage as a difference of potential in the battery. What we don't measure is the actual potentials of the anode and the cathode of the battery. And those actual potentials are what drive the electrochemical reactions, like degradation of the electrolyte in the cell, that lead to reliability, degradation, safety issues. And so this is a theoretical study done by Candler Smith and C.Y. Wang a few years ago, basically saying, well, today we set our control limits on a battery based on the voltage, because that's all we can see. But that's an overly conservative design because we don't actually know what the actual potentials are of the electrodes. If instead we could monitor the potentials of the electrodes and set our control limits based on the specific electrochemistry, the potentials happening inside the battery, what this shows is this is the operating region, state of charge swing that you'd be able to operate for the power capabilities you need for this hybrid pack. And what this shows is that in this dotted line, this is the case of actually running the pure potential limits and the side reaction limits for electrochemistry. What you see is you can extend the operating range by almost twice the energy capability of this pack. So you get almost twice as much energy swing out of this battery pack. And meanwhile, you can also increase the power capability of the pack. just by being able to know what are the potential limits and run your control algorithm based on that. So that's a really interesting, removing the blinders around potential inside the pack. Now here's one that most people would say, well, how would you possibly remove the blinders around mechanical things happening inside the cell, right? So some of the most egregious or some of the most feared defects that we have are internal shorts. This could be an internal short that came from a manufacturing defect, or it could be an internal short that comes from a process known as dendrite formation, where we basically drive an overpotential on the negative side of the battery. Rather than intercalate lithium into the anode or into the negative electrode material, the potential is such that we prefer to actually just plate lithium, right? Grow pure lithium metal as a filament on that electrode. That filament, if it grows far enough, will short the battery. And this is what can lead to these catastrophic thermal runaway and explosion events, okay? And so at first we thought to ourselves, well, there's no way you could ever detect something like that inside of a cell. And one of the things that's exciting about ARPA-E is we're funding a lot of different innovations across the space, and so we can learn from other programs. So this is an example of something we learned from our GRIDS program. We have a project in GRIDS that's looking at a macro-scale battery that's a zinc-based battery, zinc manganese oxide. And zinc has a similar problem as lithium, where you can grow dendrites in zinc. And that's what we're seeing here in this video. This is charge and discharge. You see in charge, the dendrites are growing, and in the discharge, the dendrites are shrinking back. But slowly, cycle by cycle, the dendrites are getting closer and closer to shorting out the battery. Now, in this case, the battery is macro scale, so they're actually able to put an optical microscope up and literally just watch the dendrites grow. And instead of the design constraint being, okay, we'll design this thing conservatively so we don't go and grow any dendrites, in this case, they're saying, you know what, we don't care if we grow dendrites. That lets us push the operation and get the best performance out of the device. What we care about is that the dendrites never short. And so as long as we're watching the dendrites and can see that they're about to short, we can stop the operation of the battery when the dendrites might short. And in this system, they actually found a way to remove the dendrites. So what you're seeing here is that you have electrolyte flow, which is getting rid of all those dendrites. There's an action that can be taken, and then you can continue your operation of the battery. I don't think anyone's ever asked themselves, is there a way in a state-of-the-art high-energy density battery like lithium-ion to be able to see dendrites as they're forming, and how would that increase the degrees of freedom of how you operate the battery and the performance you get out of the battery if you could do that? It's one of the exciting questions that we're asking in the program. So I mentioned a number of ways. If I get a second slide here. Okay. So I mentioned the seed for us in getting excited about AMPED was the question of, could we remove the blinders on what's happening inside the cells? And so now what I want to show you is we realize that that's probably not enough to solve this problem. And when we look at the battery management systems, we have to think about the full battery management systems and what innovations have to happen across the whole system to improve the situation. And so this is basically a battery management system kind of formulated as a traditional control loop, where you see we have the battery, we have certain measurements that we take on the battery that are going to be state inputs for a model to determine and estimate the state of the battery at any given point in time. We'll estimate the state of the battery. Then we have control algorithms to decide how we're going to use, right, how we're going to operate the system. And based on those control algorithms, the system will take some actuation, right? And so what we talked about first in terms of opportunities was the measurement side. Okay, so in today's batteries, sensing only provides indirect state information, very low spatial resolution, and we basically make all of our decisions based on that. We talked about what can you do if you improve those state inputs. Right? Another opportunity for improvement is today we take the indirect state information and we put it through a battery model to decide to estimate the state. In today's systems, generally that model is a very simple equivalent circuit model that's heuristically parameterized and validated, and it doesn't really represent the physical phenomena happening inside the cells. So what we realized is we can do better by having better state information, but we could also do better, or in tandem, we probably need to update the models so that we're actually using models that are reflective of what's happening inside cells. Better models can basically get us to the same point, which is a better estimation of what's happening inside the cells and the state of the cells. If we move down the line, we look at the control algorithms. And so in today's battery systems, we have very simple rule-based controls, and the control windows are pretty static, right? One of the things we want to do in AMPED is not only expand the windows of operation of these batteries, but also make them smarter, make the control smarter, so the windows of operation don't have to be static. They can be dynamic based on specifically what's happening in the battery pack, right? And based on what's happening outside the battery pack. I'll talk about that in a minute. Finally, if you have better information of the state of the batteries and you've decided you want to control things differently based on that information, you need a system which can actually implement the controls and have some actuation. Today's battery systems are very passive. And so to be able to have this vision work, we would need to move to more active systems where we could have better control over what's happening at the cell level, as opposed to just have simple off and on options. So I mentioned to have the control, to optimize the controls of these systems, knowing what's happening inside the cells might not be enough. We might also have advantages of understanding more about what's happening outside the cells. So let me give you a couple examples of that. This is the example of load. So what we have here is data from NHTS on basically how do people drive. And this is the probability density of the number of miles on average driven a day by a big consumer. And today when we design a vehicle, what we say is, okay, well, we probably want a 30-mile range because we'll be able to access, this percentage of average drivers out there, et cetera. Right? As you all know, right, designing based on averages basically means that you don't get optimization for anyone. So the example here is, if we look at some other data, this is a TCS real-world driving patterns. These are specific driving patterns, and they're going to populate in here as we go. But what you see is that, right, the specific driving patterns of any individual on any day are very different. We all drive vehicles differently. So we need to ask ourselves, why is it that we design an electric vehicle, we build the vehicle, and set the control rules for that vehicle once. We sell 1,000 of those vehicles to 1,000 different people who all drive the vehicle differently, right? So obviously we're not optimized for any of them. So what if we had better information about how the vehicles were going to be driven? That might seem far-fetched, but here's an example from Ford, basically thinking about a more intelligent car that says, well, vehicle says, good afternoon, Ryan. Are you headed home? And Ryan says yes. And in this case, they talk about the vehicle saying, well, there's a good driving zone, or you can avoid traffic by doing these things. We could also use the information that Ryan is driving the vehicle to basically optimize the control of the battery system for that vehicle to increase the performance without risking safety and lifetime, etc. To take it to the next step, we can imagine a future where we have autonomous vehicles. So this is an example of the Google autonomous vehicle. And in this case, obviously, we've now got a completely deterministic or an almost deterministic load because the computer is going to decide how the car is being driven. There's really not going to be human intervention. And so now we can really do a good job of optimizing. So load is one idea. And in AMPED, we are looking at integrating predictive loads into battery management. Another one is environment. So similar story, we build one vehicle, we sell it to 1,000 customers, but those 1,000 customers live in different parts of the country. There are different terrains, there are different weather patterns, right, different mean temperatures. And so couldn't we do a better job of having a more flexible control scheme to optimize for each of these folks in different areas? So I think the point is made at this point. We talked about being able to see what's happening inside the cells and respond, see what's happening outside the pack in the environment, and respond. And so what occurred to us as we continued to think about the AMP program is what we really are interested in is the following state. And this is directional, right? This is something we aspire to. We'll never be able to get. But this is the idea. Could we have full situational awareness and response? And so to really optimize what we're doing, have the right size systems instead of oversized systems, we'd like to understand what's happening inside the cells. We don't have a lot of insight into that today. We'd like to have an understanding what's happening outside the cells, the operational state. We don't have a lot of insight into that today. At least it's not getting into the battery management system. But we also need awareness and an ability to respond to a couple other things. The main one I'll point out is we need to understand actually how the cells are being degraded, right? Because if I come up with the optimal control strategy, I have to say, well, for any given control decision I make, how is that going to impact the degradation of the battery so I can optimize it? And today we don't actually have a great understanding, or at least not a very powerful, flexible understanding of how specific actions on the battery affect the degradation. So we need better insight into degradation. I'll give you a few examples of why that's important. And so this is kind of awareness and response, but now in the state of health of the battery cell. So the picture here is just meant to show a pretty typical scenario that would happen today. You get into a fender bender with your car, and with a conventional combustion vehicle, that's not such a big deal. You exchange insurance information, both drivers go home, and you get it sorted out. When we think about this situation for an electric vehicle, we say, okay, there was a fender bender, and so we know there was an impact to the battery system. But how do we really determine what damage that fender bender had on the internal operations of the batteries? Right? Today, we don't have any great tests to be able to do it, so we have to kind of make a call. And in most cases, you'll make the more conservative call because you don't really know what's going on inside the cells. And so you basically say, okay, we're going to have to replace the entire battery pack, right? What we really need is a way to say, okay, we can actually diagnose what the state of health of the battery is. And this is just one example. There are a number of examples of how that will make the economics of electric vehicles or storage generally more attractive and more efficient. Here's another example, right? If I decide to sell my vehicle today, someone looks up on Kelly's Blue Book and, does a quick check of the vehicle and decides, okay, this is a reasonable price for the vehicle. If it's an electric vehicle, now the consumer buying the car has to think about, well, how worn down is the battery pack? And what is the residual value of the battery pack? Today, that's a very hard question to answer because we don't have a great gauge of state of health. So this would be another area where we could, again, remove the blinders, make the economics and the performance more efficient and effective. And finally, I mentioned this before, dual use of batteries, right? In order to decide that it's worth it for me to sell electricity into the grid, I need to know what effect that's going to have on my battery pack, both from a diagnostic standpoint, but also from a prognostic standpoint. What's going to happen in the future if I decide to give the grid 100,000 short cycles over the next 2 years? So hopefully you've gotten a sense of the vision and what we're trying to sort of open up and illuminate in terms of new technology vectors and new capabilities in AMP. I'll just give you a snapshot of the projects that we're funding under the AMP program. And they generally match the areas that we talked about in terms of the control group and then the diagnostics and degradation prediction. So we've got a number of projects looking at sensing, things that we talked about like internal cell temperature. Could we integrate that in real time in a battery system? But also new modes of sensing like strain. Could we monitor the strain of the battery? We've got a couple of projects who are saying let's get rid of the traditional BMS and actually replace the traditional BMS with a fiber optics-based BMS. It could potentially give us much more sensing capabilities at a lower cost and open up new modes of sensing like optically scanning inside of cells in a battery to be able to see things like dendrite formation. Really exciting, entirely new focus area for the community. A number of programs thinking about modeling, better models, and more dynamic a number of projects on the system side, looking at more flexible system architectures, both on the power side, being able to differentially operate optimally different cells within a pack, but also on the thermal management side, looking at new communication strategies, etc. And then finally, a couple of really fundamental capabilities on how can we do better at diagnostics. Now, the thing to keep in mind is at ARPA-E, we only have a limited amount of money, and we run a solicitation to try and fund what we think are the highest potential impact projects that apply to the program. But the problem we're trying to solve is a much bigger problem, and our goal at ARPA-E is to solve the problem. And so we'd like to support not just these projects, but we'd like to support the entire community of folks that are trying to address this problem. And so if you're someone who's doing work in an area that's related to the AMP program, and you're interested in seeing if your work might be valuable in the context of AMP, please get in touch with us. We'd be happy to bounce some ideas around, learn about the project, and help you get integrated into the group of folks who are really working on solving these problems. So that leads me to my last point, which is one about community. This isn't just about projects, this is about building a community. And so what we found in AMPED was the problems we're trying to solve really require very multidisciplinary backgrounds. So in AMPED, we've got battery experts, but they alone can't solve the problem. We need diagnostic experts, we need control experts, and power and thermal experts, all thinking about the problem. What we found were that these different communities were looking at different aspects of this problem, but by bringing them together, we're really opening up a whole new way of trying to address some of the issues that we're facing in battery management systems. We're also bringing together different types of organizations, universities and national labs working with businesses, small businesses, and large corporations. So we have an exchange of research and folks who are focused more on the implementation side. And then even within the government, we're bringing together different groups. So ARPA-E is obviously running the AMP program, but this is a collaboration with other parts of the Department of Energy, but also the Department of Defense that has a really strong need for better control and optimization of their battery systems. And of course, private industry through the different corporations that are involved in the projects and might potentially be the funders of these projects moving forward. So hopefully you enjoyed this summary, this overview of the program. There's a lot more information on our website. There's a whole program page for AMP with descriptions and contact information for all these projects. And if all else fails, please feel free to get in touch with me anytime. My email address is here, and we'd be really excited to engage you in this effort. Thank you very much.